Okay, here we go. Look at week 9, day 1. Let's talk about the discussion section first, and we're going to talk about algorithms today. So, everybody who submitted a essay for the discussion session has 2 peer reviews assigned to them. If you didn't do the essay, you can't do the peer review. This is how it works. So, under the discussion section, corporate censorship discussion, click there. And in the top right corner, you'll see some drop-down things. It might look a little different for you, but it's called peer reviews, and that will show you who your peer review is. If not, you'll see it, I don't know, some other way. And it'll give you 2 people to review. You only have to review 1 of them. What you have to do, you have a week from today to do it. And what you have to do is this. So you must disagree with the person that you're responding to. Okay? So you must make a counter argument. So in order to counter an argument, there's only a couple different ways you can counter an argument. And remember, you must be respectful. If you are disrespectful to the other person, if you make a personal attack, be very careful with humor. Like I said last year, some guy was like, "Yo, I just gotta say, you're totally wrong, dude." It's like, no, like don't do that. Like, what you should do, there's really 2 ways to disagree with somebody. First of all, you can go through the references and see if a reference doesn't actually say what they say it's saying. If they say this reference shows that, more Americans die of shark attacks a year than, get coronavirus, and you look at the reference and it doesn't actually say that, mention that in your response to them. Okay? So actually, it's your job to go through each of the references and check the references and make sure they're saying what they claim they said. If they don't have any references, that's an easy attack. Just say you made some claims, you didn't provide any references for them. Pretty easy. So remember, you're supposed to provide 3 references to back up your points. It's not 3 references per question, just 3 references overall. There's no formatting requirement. I don't care if it's MLA or what. Like, normally I would just expect people to just paste the URL. But, you can use a whatever sort of format you want for the references. So go through the references, make sure they're saying what they're saying. The other way you can attack an argument is if the logic doesn't flow. So if they claim that it's very important in a free society for the government to allow everyone to speak their mind, therefore corporations should allow people to speak their mind. That's not a logical connection there, because corporations are not a government, right? If your basic principle is government should allow freedom of speech, therefore corporations should allow freedom of speech, there's a missing step in between, right? Because corporations are not governments. It's not the same thing. So look at the flow of the logic, and you're gonna write a paragraph or 2. That's it. It's not an entire essay. Just say what they did well, say any mistakes they made, and then finish by saying something else they did well. It's the hamburger method of disagreement, right? So say something you liked about it, find a point of disagreement. You should be able to find at least 1 point of disagreement where they made a mistake in everything, and then finish by saying something else. Overall very well written, something like that. Just compliment them. Okay. Where do we post replies for the peer reviews? You reply to the person. So if you click on, like if you were assigned Octavio's essay, I'm not going to show it here, but if you click on Octavio's essay, then you hit reply to it, and you reply. And you only need to do 1 reply. If you literally can't find any mistake in the person's thing, maybe look at your other one. You're given 2 to pick from. But basically, you just hit reply and reply there. And then a week from today, I'm going to go through and read everyone's essays and read all the responses and give you guys the points for it. Okay? So, yep. Any questions about the You were given 2 students to peer review. Is that supposed to happen? Yes. Everyone's given 2. You only have to do 1. Okay. Resources, logical mistakes, sandwich with compliments. That's correct. Yeah. So check the references. Check to see if the logic flows. Yep. You only have to reply to 1 of the 2 you're given. That's correct. Yeah. Sometimes somebody will just not really write an essay, and there's not really much you can say. So you're given 2, just in case one of the people said, I don't know, man. Okay. And... yeah. Okay. Okay. So that is our discussion, and we'll probably do another one of these in, after the peer reviews are in. Okay. So there's lots of very interesting topics to talk about where technology and society, collide, right? We've never had a situation like this before where like a few companies control what people can say to each other, right? Like imagine if every tech company in the world wanted to cancel you, right? Can't post on Twitter, can't post on Facebook, can't make a phone call because the phone calls all go through, a tech company. What are you gonna do? Write a letter? It's what are you gonna do? Go to the town square and with a billboard? I don't know. What are signboards? It's it's a different world we live in, and so I'm not taking any stance myself on the matter because I don't have a good answer for it. I just think that we as a society need to talk about these things. I think it's really important that we have conversations about possible problems, actual problems, possible solutions, actual solutions. Okay. So I think it's actually very, very important that these discussions take place, not just here for this class, but in society overall in general. So that is that. Okay. How long till the Terminators rise? Yeah. Right. So let's talk about algorithms. So we haven't done programming in a while, so let's hop over back into Scratch to MIT.edu. If you guys want, you can. Do you guys want to see some of the storybooks that you guys shared? Can the government have a tweet removed? Yeah, that's an interesting question, right? Like, what would it take for the government to order Twitter to remove a tweet? That's an interesting question. Let's see if I can find one that I liked. Actually, there are a lot of them that I liked. Storybook, go on. Let me click on it. There we go. Untitled Copy. Well, that's a fantastic name. Yeah, that one. Yeah, Mario had some nice art assets. Let's just show that one. So you can see that they had some pretty good art, brought in, and there's a few people that had some really nice art. On it. Yeah, Twitter has been banning people that post the word Memphis, which is really funny. You can see here. You can see that the art isn't transparent, right? So the you can set art to be transparent. Stop. So you see how there's like a white background instead of a transparent background? That's something that can be fixed. Okay, anyway. Let's go do a new one. Create. Let's talk about algorithms. So, what is an algorithm? An algorithm is a step-by-step way of solving a problem. Okay? So, a step-by-step way of solving a problem. So, if you were to have a maze, if I were to give you a maze, and let me go into OneNote, talk about this. 3:15, 21. Algorithms are step-by-step ways of solving problems. So, given a problem, your solution is called an algorithm. Okay? So let's pull up a maze here and think about how we might solve it. Starting square, and then we'll have some obstacles here. Some obstacles here. Right. Ending square here. Right. You know, a maze. So you got to start there. You got to in there. How do you program a robot to navigate a maze? Right. How would you do that? You know, think about it. How do you solve it when you're a kid? Right. You just try every possible, you know, route. Is there a better way? How do you guys do that? How would you program a computer to solve the maze? You know. Yeah, I'm not criticizing the up. Sorry, I'm just saying like there's ways you can cut out the white background. It's not bad. I'm just noting that. Mash buttons on the keyboards. So I see that you play Eddie on Tekken. How do you solve it? Like what, you know, if you were to be given this as a programming assignment, how would you write a program? Like, you know, just use English. You don't have to know how to program because this is Seaside 1. You're not expected to program, but how would you do it in real life? Some maze, and you need to solve it. Check every input. So check every square, I assume you mean. So from the start, you check north, south, east, and west. Right? You check up here. Oh, that's outside of the maze. So that's one possibility, right? It's outside. You know, it could be outside the maze. It could be open. It could be a wall, like here. And then, yeah, that's about it. Maybe there could be a fourth option. Felt like been there before. And so out of the starting space here, there's only one open square, so I guess we'll go that way, right? So we'll go to this square here, and then repeat. Okay, this way is out of the maze. The place to the left, we've been there before. Place down here is a wall. Place to the right is open. Okay, I guess we'll go here. And then you like mark this as like we've been there before, right? And then that's outside, that's a wall, that one we've been there before, that one's open. So far so good. Come down here, mark that. Oh, now we've got two opportunities, right? So the one to the south is a wall, one above, we've been there before, but now we got two opportunities. So what do we do? Right? What do we do? Do you go left or do you go right by default? Right. Flip a coin? Okay. So let's flip a coin. Let's say we come this way. So we're coming this way, and we're coming this way, and we're coming this way, and oh dear, we've hit a dead end. Now what? You know, you can't go back here because you've been there before, right? So you're completely stuck, right? So you've checked all possibilities. North is blocked, west is blocked, east is blocked, south is blocked. Or at least we've been there before. So you need to do something like maybe remember where you had that last branch and then go back to it, right? So you had a branch, one approach was going right, and then that one didn't pan out. So then you walk back to where you were before, you walk back to here, and then you try this way, right? And so having some sort of record of where your branches were, and if one branch doesn't pan out, going back to the last branch spot, and then going the other way, you know, one way you can solve the maze, and that in fact will, you know, will do it. That would be the algorithm. So an algorithm to solve a maze could be written something like this. Check all directions from the current square. Okay, so this is how to solve the maze. There's a lot of ways to solve a maze. This is just one. Okay, so you check every direction. If there's only one option, take it. Right. So if there's only one way to go, we go in that direction. Yeah. Before we take it, we should mark our square as being visited. You guys know the story of Theseus and the Minotaur, who walked through the maze dropping breadcrumbs behind him to indicate where he'd been. So the breadcrumb would be a mark, where you have a chalky, write chalk on the wall to show that you've been there before. Mark your square as being visited. Then if there is only one option, go there. Otherwise, flip a coin and write down where you flip the coin. So if there's two or more options, write down where you flip the coin and go that way. And if there are no options, go back to where you last flipped a coin. And of course that wouldn't be a coin if you have 3 branches you could go to, but principle remains. Roll a die, whatever. Okay, and so that algorithm right there, step-by-step set of directions, is enough to solve any maze like this. Okay. So you basically write down, you mark, you get out your chalk, mark up the spot you're on, and then pick a random direction to go in. And if you ever hit a point where if there's only one option, you go in that direction. If there's two or more options, you flip a coin or roll a die and go in that direction. And you write down like the last place that you had a fork in the road. Right. So if that spot here was where there was a fork, that is column 3, row 3. Column 3, row 3. So you write down there's a fork at 3, 3. And then the thing would start going that way, and then that way, and then that way, and that way, and it gets dead-ended. So then it consults the table you had here. The last time there was a fork, there's a fork at 3, 3. All right, so we backtrack to there, and then we go the other way. And you go the other way, and coming around this way, and maybe you come to another fork where you can go up or right. And so this might be column 7 and row 2. So we would write down there's a fork at row 2, column 7, and then maybe we keep going. We hit the exit. All right, cool. Oh, that was one thing I didn't say. Like, what happens if you hit the exit? 6. If exit, done. That should probably be up here somewhere. Okay. And also, what if stuck? Done also, right? So how do you know if you're stuck? That should probably be up here somewhere as well. It doesn't matter. Great. So how can you figure out if you're stuck? Like, what if the maze looked like this? What if there's a trap? What if there's a minotaur? Okay. How could you figure out if you're stuck or not? Like, in other words, stuck meaning there's no solution to the maze. How could you detect if there's no solution to the maze? You've been to every square? No, because like there would be a square here, right? There's a square here that we haven't been to. We can't get to it. Is the YouTube still live? It should be. Yeah, the YouTube is live. Yeah. There's currently 5 people watching it. So how do we detect that we're stuck? That we have no options left to go to? If you've gone through every branch, yeah. Mm-hmm. So if you, let's say we came to this branch here. This one went down here and got stuck. Okay, so it backtracks back up to here. Then it takes this one. Then it has another fork and it goes to the left. And that one's stuck. And it goes to the right and that one's stuck. And then it tries backtracking, but there's nowhere else to backtrack to. If your list of all the different forks is empty, there's nowhere left to go to, and that's it. You know, or technically, let's see, you'd backtrack to like here or something. You'd backtrack to like here, and then there's no possible directions to go to, and then that's it. You'd be like, maze is unsolvable. Mission completed. You've explored the maze. Yeah, and you can have multiple forks written down, right? Because, you know, if you get to this spot, that's a fork. And you get to this spot, and that's a fork. You get to this spot, and that's a fork. So you can actually have, like, that'd be like row 4, row 4, row 5, row 6. And so this thing would actually have, like, row 4, column 1, row 5, column 1, row 6, column 1. Now let's say you go to the left here. Then it would... you know, actually probably, it'd probably go up like this, and then backtrack back to here. And as you backtrack, you erase the bottom option, and then it would start going to the right and start marking these squares off. And so you can actually have multiple things to backtrack to. And so if you got stuck here, it would actually backtrack all the way back to here. And then you're stuck, and so it'd backtrack to here. And so once your list of forks is empty, then, and you're stuck, that's it. Game over. The maze is not solvable. And so if that was hard to wrap your mind around, yeah, it's not an easy problem. It's typically a problem given in second semester computer science. You don't have to program it right now. You're not going to have to do it in Scratch. The point is that that would be an example of a moderately difficult problem to solve in computer science. Okay, so this is computer science 1. This is a easy class, right? I'm not going to make you solve a maze. But I want to go over algorithms. Okay, so that would be an example of a step-by-step series of instructions to solve a problem. The problem is get a robot through this maze, and these steps here would be an algorithm to solve it. It's not in computer code; it's just in English. But anytime you followed a recipe, like if you've cooked.
I don't want to solve it before we solve.
Okay. If you've ever followed a recipe when cooking, that's an algorithm. It's a step-by-step series of instructions, and it should be as clear and straightforward as possible. There's some funny YouTube videos you can watch where, like, the father will have his daughter write down instructions on how to make a peanut butter and jelly sandwich, and he ends up putting the bread on his face, things like that, because he interprets everything overly literally and stuff like that. So another classic example of an algorithm is sorting. So if I give you 7, 1, 9, and 3, how would you sort that? How would you sort those numbers? One, 3, 7, 9. Interesting. I didn't tell you lowest to highest. I just said sort them. So, and this would be sorted, right? It's ambiguous. And so, in computer science, one of the biggest challenges, if you work as a professional programmer, which I could talk about some other time, is getting from your client, whoever it is that's paying you to do the programming for you, getting them to actually specify what they want. That's actually oftentimes the hardest thing, right? Like, I'll do what you want, man. You just need to tell me what it is you want, and they don't know. Just make me an app. For what? What do you want it to do? It just needs to connect me with my customers. What does that mean? Do you want, like, an instant messaging system? You want me to read you Facebook? Like, what do you mean connect you with your, Well, it needs to do coupons. Like, okay, like, how? How do you want it to do coupons? Do you want it to be text-based? Like, like, hey, come into BJ's Pizza today, it's $5 off. Because BJ's Pizza has their own app, right? Yes, they did the last time I checked. Android store. You'd be surprised how many people, like, if you're a programmer, you'll be surprised how many people want you to make an app for them, BJ's Pizza. There you go. And so it's got a restaurant finder, so you can find the nearest. There's only one in Fresno. So somebody will want you to make an app for them and have no idea what they actually want, really. Or they have some vague ideas and they don't really know. And so dealing with that is honestly one of the biggest headaches of being a programmer. Is like, all right, you need to tell me exactly what you want. And they're like, I can't do my job for you, man. I'm like, man, my job is to program it. It's your job. You're the person trying to design the thing. You need to design it. Okay, so anyway, sorting. So how do you sort? So just do the thing that does the thing. Yeah. Thanks. And a lot of times they just don't know. They don't know exactly what they want. They just have sort of a vague idea. And then you do something and they're like, no, that's not what I wanted. I'm not going to pay you. Right. So you have to be very careful with your contracts and have a contract so that you'll get paid even if they don't like it. Or the contract specifies more precisely, I will do X, Y, and Z. If I do X, Y, and Z, I get paid. And you can do milestones. Like if I do X, I get a third of it. If I do Y, I get a third of it. I do Z, I get a third of it. So you get paid along the way. Getting that first check out of them is the hardest also. So try to set an early milestone so you get paid early. Just so, they're not going to come to the end of it and be like, no, I'm not going to pay you. That happens. Okay. So how do we do sorting? So if I was going to sort this lowest to highest, one approach I can do is to find the smallest number. Find the smallest number. Pull it out. Whatever that means, not very technical. And 3, repeat. Repeat. Repeat until empty. So, being a little bit vague here, but so let's do this. So here's our input. Find the smallest number. All right, the smallest number is 1. I'm going to pull it out. All right, cool. So I erase it out of there. And I put it over here. Cool. Repeat until empty. All right. Next smallest number is 3. And I pull it out. And I put it over here. And I repeat until empty. Next is 7. Next is 9. The input array is now empty, and we're done. So we've now sorted it smallest to biggest. Do you guys understand? Yelp remake with a subscription. Yeah, just redo Facebook. It's easy, right? Facebook's not very difficult. Yeah. So what components would go into this? So there's actually a couple different things that go into this. So we got some if statements in here, got some conditionals in here. Finding the smallest number itself is a loop. So finding the smallest number says start at the beginning, going to the end, and write down whoever the smallest person is. Is this bubble sort from Java? It's insertion sort. Or selection sort. It's a bad algorithm, by the way. We'll explain why in a second. So, do you guys understand how finding the smallest number, let's see, how that works? Like, you've got your input array, and you've got 9, 7, 3, 1 in it, whatever. So to find the smallest number, you start at the first element. Like, all right, the smallest person I've seen so far is 9. And then you go to the next one, and you're like, oh, I found somebody smaller. You write that one down. Let me put these in a different order. It's a little more interesting. All right, I found somebody smaller. Cool. And then we go on to the next element. And we're like, oh, found somebody even smaller. Found this one person. Cool. And then we go on to the next element. And is that smaller? Nope. Okay, so the smallest element is 1. And so we pull that out and put it over here and repeat. Okay. So if I had 1 million numbers in this array here, I would have to start at the beginning and go to the end. And so I'd have to do 1 million comparisons. Do you guys understand? So if I had dot 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 1,000,000 elements, and then at the very end I had negative 100, which would be the new smallest one. Do you guys see that how this step here would do like 1,000,000 operations, 1,000,000 steps? We'd have to start at the beginning and go to the end to find the smallest element. Do you guys see that? Like this thing here is not one step, right? I'm giving it to you in English, find the smallest number, but in order to find the smallest number, you start at the beginning, and you go to the end. And so if it's a trillion, if there's a trillion numbers, you're going to go like, all right, element 1, element 2, element 3, element 4, element 9 million, element 10 million, element 999,999,999,999, you know. Do you guys see that? Sounds repetitive, sure. It's a lot of work. And so if the size of this input, let's say the size of the input is n, how many comparisons would you have to do for just step 1? Coding is full of repetition and loops. Yeah. Remember what we talked about last time. The only tools you have in computer science are if statements and loops and algebra, comparisons, you know. That's it. There's very few things that actually make up computer science. You got variables, you got algebra, you got branches, conditionals, if statements, whatever you want to call them. You got loops. That's about it. You got things that I/O, I guess, input and output, and then you've got other ways of organizing those things into things like functions and classes and things like that. There are ways of organizing them, but that's it for the basic tools. Okay. You have to read all the numbers first, yeah. So finding the smallest number is in work. Do you guys understand? So to find the smallest number, you have to go through the whole thing. Pull it out. That's pretty easy. You just erase it and put it into another array. Simple. That is one work. Now, repeat until empty. So how many times are we going to do this repeat? Okay. How many times are we going to come back up here and do it again? How many times are we going to repeat? If we've got 1,000,000 numbers, how many times are we going to repeat? One million times. Very good, Catherine. Yeah. So 1,000,000 times. 1,000,000 times, we're going to do 1,000,000 work. So how much? So if our input size, which we call n, if our input size is 1,000,000, the amount of work we have to do overall is 1,000,000 times 1,000,000. So 1,000,000 times we're going to do 1,000,000 work, because we're going to repeat this 1,000,000 times, right? We're going to repeat, because if you have 1,000,000 people in the input, you're going to pull out a person and do it again, and that's 1,000,000 more work to find the next guy that's smallest, pull it out, do it again. You're going to repeat it 1,000,000 times. So 1,000,000 times you're going to do 1,000,000 work, which is a trillion amount of work. The total amount of work we would do if the input is 1,000,000, the amount of work we would have to do is a trillion. Okay. What if our input was size 1,000,000,000? Then for step 1, to find the smallest element out of 1,000,000,000 elements is how much work? So if you had to find the smallest element out of a billion numbers, how many steps is that? A billion. Good. And then how many times you're going to repeat? Because you're going to keep repeating. You're going to do step 1 over and over again until it's empty. So how many times are you going to repeat? You're going to repeat a billion times also. Good. So a billion times, you do a billion work. So how many steps is that? If the input size is a billion, 1 billion, you're going to do 1 billion times 1 billion work. What number is that? Quadrillion? Times 1,000 times a billion. Quintillion? One with 18 zeros? Getting into scientific notation now, huh? Yeah. It's a big number. It's a big number. So, what if I told you there was a better way? What if I told you that there was an algorithm that could do this quicker? Now, there's no algorithm that will beat, a billion, right? Because like somebody pointed out, there's nothing that can beat a billion, because at a minimum you've got to read, you got to read through the numbers. You know what I mean? Like you got to go through the input at least once. So you're never going to be faster than like a billion. But rather than this garbage, this is called this is what we call an order n squared algorithm, right? Because the amount of work is the square of the size of the input. Does that make sense? So the if your input is size 1,000,000, the amount of work you have to do is 1,000,000 times 1,000,000. There's a better way of doing sorting. And a better way of doing sorting would do this in about 20 million steps. And the better way of sorting a billion numbers would be 1,000, million, billion, inverse log base 2 of that is 30. Okay. 30 billion. Okay. So just by designing your algorithm better, you can take a program that would run in 1,000,000 times 1,000,000 steps and run it in 20 million instead. So how much faster is that? Like there's a number of good algorithms this way. There's at least 5 or 6 that I could write off the top of my head. How much faster is 20 million than a billion? Anyone know? Would a binary search work? Binary search will find, if you have a sorted algorithm, you can find an element in the array quickly using binary search. It doesn't help you search. 5 times faster? So 5 times 20 million is 100 million. So, no, it's not 1,000,000 times 1,000,000. That's a trillion. Yeah, that's a trillion. So 50 times 20 is a billion. So it's 50,000 times faster. So this is 50,000 times faster. Okay, and that's just for 1,000,000. That's sorting. That's just the people in Fresno. You know what I mean? Like the greater Fresno metropolitan area and county, there's about 1,000,000 people. If you were to sort the names of the people in Fresno, if you did it using a smart algorithm versus a dumb algorithm, it will be 50,000 times faster. That's not even that big a number. 1,000,000's not even that big a number in computer science. Here, I don't know. It's like 30 million times faster, something like that. Right? It's like 30 million times faster. 30 million times faster. Right? And that's not even all the people on Earth. You know what I mean? And so it's really important to have a good algorithm. Having a smart algorithm that does things quickly, and to tell you what the answer is here, the amount of work you do is log base 2 of n times n work. So if you guys don't know what a logarithm is, it's the opposite of exponentiation. I don't know. It's something you probably studied in algebra and forgot, but take the input size, a billion, and plug it into log base 2, and you'll get like 30. And so it's 30 times a billion instead of a billion times a billion. It's much, much faster. It's incredibly faster. And I could write one of these sorting algorithms in, I don't know, 5 or 6 lines of code. It's not even noticeably faster to write than this garbage here. So, this right here is one of the most important principles in computer science, which is that if you're smart and you think about a problem and think about how to solve a problem, and you like hit upon a better solution, you can come up with a solution that is unbelievably faster than what was before. Okay? How much actual time would that 50,000 faster cutoff? Is it hard to find out? Sure, I can tell you. So at the DMV, if you guys have ever seen Zootopia, you'll probably know where I'm going with this. In Zootopia, the DMV is staffed by sloths, right? At the DMV, they had to look up my name, look up my record by name, and so they type in my name and hit search, and I stand there literally for 5 minutes while the computer is searching for my name. And I'm like, there's only 30 million people in California. It shouldn't be this slow. What the hell is happening here? And so there's only 2 possibilities I can think of. One, their system was just incredibly overloaded, which it might be. More probably, though, the system was going through all 30 million records in the DMV, right? Trying to find my name, trying to match on my name. Whereas, if they had done it quickly, they could have, Miger talked about, they could have used binary search to find my name, which would have taken 20 steps instead of, or 24 steps instead of 30 million. It would have been literally 1,000,000 times faster. And so Ramsey's, what is 1,000,000 times faster than 5 minutes? So 5 minutes is 300 seconds divided by 1,000,000. So it should have been able to find my name in a fraction of a second. They should have typed in my name. It would have been like, boom, there he is. And then it wouldn't have wasted my time. It wouldn't have wasted the DMV's time. Instead, I got to sit there, and the employee got to sit there for 5 minutes, just watching the system going through every person in California, trying to match me. Okay? And so, that would be a real-life example of, if you have a bad algorithm, it can be annoyingly slow. Whereas if you put a smart computer science person in there, or you don't even have to be smart, it's just think about it for a while and see if you can come up with a better solution. You can make a huge real-world difference in the running time. Are you going to be quizzed on this week? This might be a little hard for you to be quizzed on. So I'm going to go with no. I think I'm not going to quiz you on. Maybe I'll give you a maze to solve. No, I'm kidding. So. That says fork, by the way. That's an O, just so you know. Okay. No, we're just talking algorithms. Your next assignment, Alejandra, is going to be. Well, we'll get to that next time. My current idea is to have you guys make Space Invaders. It's not really an algorithm though, so I might come up with some more algorithm-y thing to do in Scratch. What I did the last time I taught it was I had people go onto a website where it shows you how to make Space Invaders in Scratch and just follow it step by step, which might be it's a pretty easy assignment, honestly. But since we're talking about algorithms this week, I kind of want you guys to do some sort of algorithm in Scratch. So. Will there also be a textbook reading? Yeah, we just finished one, so I'll look at and see if there's any topics that are relevant to this on top of it. Yeah, so you got your peer reviews. Peer reviews are due next Monday. Other than that, there's not going to be a quiz for today. There will be a programming assignment probably given out on Friday is my plan for that. So we'll talk a little bit more about algorithms and programming. What's the takeaway point from today? An algorithm is a step-by-step series of instructions to solve a problem. That's your takeaway. Okay? And Some algorithms are better than others. Okay, so this way of solving sorting works. It's correct. It will correctly give you a sorted array, but it will be 30 million times slower. 30 million times slower than a smart algorithm. If you're sorting all the people in China, you can do it the dumb way or you do it the smart way. So be smart. Okay? Are there simpler ways of solving? What's the best algorithm? There's a series of best algorithms. And there's quick sort, merge sort, heap sort. Radix sort is kind of... don't worry about it. But like, there's a number of algorithms that all will have about this running time. And so what people do is they'll implement it. They'll implement all three of them and see which one's faster in practice. If that makes sense? And pick that one. So they're pretty easy to write. All three of them can be written actually pretty easily. So, maybe even easier than the dumb algorithm. You could code it really fast. And you'll get a real world massive difference in runtime. You can either be the DMV or not, and that's your choice. Okay, so we'll stop it there. Okay, that's it for today. Those are the two takeaway points. Right. I'm supposed to make something similar to Space Invaders. Just the review for today. That is it for today. Yeah, that's it for today. So do your peer review. That'll be due next Monday. Okay. What situations is the slower algorithm better? Good question. So before you guys peace out, Mary has a really good question. Are there times when the slower algorithm is better? And the answer is yes. So bubble sort, which is not this, but has this kind of running time. Bubble sort has a garbage order n squared running time. Bubble sort turns out to be faster if you give it a sorted array. So if the input, Mary, if the input to the array is already sorted, bubble sort goes through, goes bloop, 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 sorted, done, and then it quits. And so if you pass a sorted array or an array that is almost sorted to bubble sort, it can actually sort it faster than the fastest arrays, sorting algorithms. So in edge cases like that, there are faster solutions. So true story. In fact, quicksort, which is normally the fastest sorting algorithm, is actually slowest if you pass it a sorted array. So bubble sort will beat a... So don't sort it twice. Don't worry about that. You don't have to know that for this class, but it is a good question, and there are all sorts of really interesting answers to these things. Okay, so we'll call it there. Have a great day, everyone.